With just one machine, China has turned a 7-hour mountain drive into a 20-minute journey, powered by engineering intelligence and sheer mechanical force. The Tianshan Shengli Tunnel, the longest expressway tunnel in Asia, spans over 22,000 meters, cutting straight through mountains that rise more than 3,000 meters above sea level. It is not only a symbol of human ingenuity, but also a true battleground where 3,000-ton super machines confront nature head-on. How does China achieve such rapid progress in building mile-long tunnels through mountains? Is cutting-edge technology the answer? Or does true sustainability still depend on working with nature? In this episode, Massive Minds takes you straight into the heart of Asia and determination. Before enjoying this topic, please consider subscribing to support our team and give us the motivation to produce more interesting videos. Hidden behind the breathtaking beauty of northwestern China's mountain ranges lies a harsh reality. According to statistics from the Ministry of Transport of China, more than 1,000 deadly landslides are recorded each year along mountain roads. These are narrow, winding routes carved into steep slopes, where a single mistake can turn an entire convoy into wreckage. In Xinjiang, a vast region covering nearly 1/6 of China's total land area, transportation was once a constant struggle. To cross the Tianshan Mountains, some mountain passes stretched over 200 kilometers, taking up to 7 hours to complete. Drivers faced hundreds of sharp hairpin turns, elevation changes exceeding 2,000 meters, and danger in every season. Each snowstorm could trap hundreds of vehicles. Each heavy rain could send torrents of rock and soil crashing down the mountainsides like invisible blades. Those cold, unforgiving numbers left no room for hesitation. There were only two choices: continue gambling with human lives against nature, or find a way to overcome it. The Tianshan Tunnel was never just a transportation project. It was an answer to a life-and-death question. How do you connect a region torn apart by extreme terrain? How do you create a safe, reliable, and sustainable transport corridor that can endure earthquakes, avalanches, and the relentless passage of time? To turn the idea of driving a tunnel straight through a mountain into reality, everything begins with a carefully built plan. From day one, Chinese engineers launched a large-scale survey program, essentially dissecting the mountain long before construction ever began. Along the proposed route, they drilled hundreds of boreholes, ranging from 50 to 300 meters deep, to collect soil and rock samples. Each sample point revealed another piece of the mountain's internal structure, allowing engineers to accurately identify fault zones, weak rock layers, and areas with a high risk of landslides. At the same time, a project of this scale could not ignore its environmental footprint. Detailed scientific assessments were carried out to evaluate long-term impacts on the landscape, surrounding ecosystems, and natural water systems. Sustainability was treated as a core requirement, not an afterthought. All of this data was then fed into advanced 3D simulation models. These digital models allowed the design teams to calculate every detail with precision and choose construction methods best suited to the geology and environmental conditions. The goal was clear: maximize safety, efficiency, and long-term reliability before a single meter of tunnel was excavated. The next critical task was to create a livable environment for people working deep inside the mountain. Why was this so important? Because the underground world is completely different from the surface. Changes in pressure, temperature, and oxygen levels can have serious effects on human health if they are not carefully controlled. To keep fresh air flowing, Chinese engineers designed a vertical ventilation system using technical shafts reaching depths of up to 702 meters. Built with raised boring technology, this method drills upward from below, allowing extremely high precision while reducing the risk of wall collapse. The drill head rotates hundreds of times per minute, crushing solid rock and carrying debris out through pressurized conveyor systems. Each ventilation shaft acts like a lifeline, delivering oxygen into the tunnel while pulling out CO2, dust, and harmful gases in the opposite direction. But airflow alone is not enough. In long mountain tunnels, the greatest danger is not a lack of air, but the buildup of invisible, odorless toxic gases such as carbon monoxide, sulfur dioxide, or methane, which can accumulate during continuous operation. To prevent gas poisoning or explosions, the entire Tianshan Tunnel, stretching over 22 kilometers, is equipped with hundreds of fiber optic and atmospheric sensors. These systems operate around the clock, monitoring oxygen levels, temperature, humidity, toxic gases, and even geological vibrations. If carbon monoxide levels exceed safe limits in any section, the system responds instantly. Jet fans accelerate, local exhaust valves open, and warning signals alert the operations team. All of this happens automatically, within seconds. This ventilation and monitoring network functions like a set of invisible eyes, protecting human life not only for workers during construction, but also for the millions of vehicles that will pass through the tunnel each year once it is fully operational. Once the necessary data was collected and safe working conditions were secured, the most complex and decisive stage began: tunnel excavation. For this task, engineers placed their trust in one machine above all others: the tunnel boring machine, or tunnel boring machine. Nearly 100 meters long and weighing up to 3,000 tons, this steel giant had already helped Switzerland build the longest tunnel on Earth, and China now aimed to repeat that success beneath the Tianshan Mountains. But deploying a tunnel boring machine of this scale was a challenge in itself. With dimensions comparable to a 30-story building laid horizontally, transporting and assembling it was anything but simple. The machine was delivered to the site in hundreds of specialized vehicles, carrying everything from the 1,500-ton cutter head to hydraulic systems, control cabins, and structural segments. To create enough space for assembly, auxiliary tunnels had to be widened and temporarily reinforced with steel frames and sprayed concrete. Each massive component was fitted together in extremely tight conditions, with an allowable error of no more than 5 millimeters. Even a small misalignment could send the entire tunnel off course and cause serious consequences. Once assembled, the tunnel boring machine became a living steel organism guided by human intelligence. The central control system, excavation modules, hydraulic thrust cylinders, conveyor belts, and cooling units all worked together as a single system. From the control room, commands were issued. Giant hydraulic cylinders pressed dozens of alloy cutting discs into the rock with forces reaching 500 tons. The mountain trembled slightly. The cutter head began to rotate, and the solid heart of the Tianshan Mountains slowly opened. Each excavation cycle advanced just over 1 meter, but that cycle of pressing, drilling, releasing, and pushing forward repeated continuously, day and night. Crushed rock was collected by conveyor belts and transported out of the tunnel, while high-pressure water jets cooled the cutter head, reduced friction, and extended the life of the cutting tools. Hydraulic locking systems opened and closed automatically to stabilize the machine at every step. Every movement followed a precise sequence. No errors were allowed. What makes a tunnel boring machine a true symbol of modern tunnel engineering is not only its mechanical strength, but its remarkable stability. Over a tunneling distance of more than 22 kilometers, the machine was allowed to deviate by only a few centimeters. Any greater deviation could send it into weak rock zones, cause ground settlement, trigger collapses, or trap the machine itself. Such a failure could cost the project tens of millions of dollars. To prevent this, the Tianshan tunnel boring machines were equipped with geological sensors, satellite positioning systems, and automated control algorithms. Based on real-time data about rock hardness and structure, the machine continuously adjusted its direction, pressure, and rotation speed. In effect, it operated like a thinking machine. This is what transformed tunnel construction from brute mechanical labor into an art of extreme precision. With stable performance and adaptive control, Chinese engineers achieved an excavation speed of nearly 500 meters per month. It is an achievement that has drawn global attention, especially as China now operates hundreds of tunnel boring machines simultaneously across the country, a scale never before seen in the history of underground infrastructure construction. But could a single tunnel boring machine conquer the entire Tianshan mountain range? The answer is no. Even with immense power and precision, a tunnel boring machine is not always suitable. In a project cutting through many geological layers, some rock is too hard, wearing down cutters, while other sections are too fragile and risk collapse under heavy pressure. When the machine can no longer advance, engineers turn to a classic solution: controlled drilling and blasting. Though it sounds aggressive, this method is carefully calculated. Dozens of small holes are drilled, explosives are precisely placed and timed, and each blast is designed to break rock only where intended. Afterward, debris is removed, dust extracted, and tunnel walls are reinforced before the next cycle begins. Preparation takes hours for blasts lasting only seconds, repeated hundreds of times with strict discipline. In the most difficult sections, the human role becomes essential. When technology reaches its limits, experience and judgment take over. Choosing the wrong rock area, misplacing a borehole, or miscalculating the blast force can plunge the entire tunnel project into crisis. Tunneling using controlled drilling and blasting is not about brute force. It is a precise technique, guided by human understanding, and remains a crucial part of modern mountain tunnel construction. To reduce risk in the most complex geological sections, China adopted a different construction philosophy, the new Austrian tunneling method, often described as tunneling by listening to the mountain. Unlike tunnel boring machine excavation, which follows a fixed and rigid path, the new Austrian tunneling method offers far greater flexibility in difficult ground conditions. Instead of forcing nature into a predefined shape, engineers adjust their approach based on how the rock and soil actually respond. Each advance is short, typically 1 to 2 meters. Sensors immediately measure tunnel deformation, cracks are sealed with shotcrete, while weak ground is stabilized using steel ribs and reinforcement mesh. These responses are continuously compared with 3D simulation models to track how the mountain reacts in real time. Inside the Tianshan Shengli Tunnel, the new Austrian tunneling method was used in weathered rock zones, fault areas, and sections where the geology was too weak for safe tunnel boring machine operation. Thanks to this approach, the project overcame major technical barriers while saving time and cost, without deploying additional tunnel boring machines for short, high-risk sections. In the most unpredictable parts of the mountain, the new Austrian tunneling method proved that sometimes the safest way forward is not to overpower nature, but to work with it, one careful step at a time. The next stage focused on reinforcing and completing the tunnel lining, a phase that had to be carried out quickly to prevent newly excavated sections from settling or being crushed by pressure from the surrounding rock. Engineers first covered the entire tunnel surface with a layer of shotcrete, typically 10 to 30 centimeters thick. This layer was combined with crack-resistant steel mesh and long rock bolts anchored deep into the mountain to lock the structure in place. Next came the permanent concrete lining. Using sliding formwork or mobile casting molds, crews built a continuous arched shell that closely followed the tunnel walls. This curved structure evenly distributed the immense pressure from the surrounding rock mass, forming the tunnel's long-term system. In areas exposed to high stress or water infiltration risks, additional protection was added. Engineers installed HDPE waterproof membranes, thermal insulation layers, and concealed drainage systems to ensure that even if landslides or groundwater pressure occurred outside, the interior of the tunnel would remain dry and stable. Every material layer, every weld, and every lining segment was closely monitored using sensors and 3D laser scanning technology, with tolerances kept within just a few millimeters. Even the smallest gap could become a weak point over time, so precision at this stage was not optional. It was essential for the tunnel's long-term safety and durability. To ensure maximum safety and construction quality before opening to traffic, every stage of the project was carefully inspected and monitored from start to finish. Inside the Tianshan Shengli Tunnel, Chinese engineers deployed a 24/7 active safety monitoring system. A dense network of sensors, cameras, ground-penetrating radar, and instruments measuring deformation, pressure, temperature, and humidity runs along the entire tunnel. Even the smallest changes are detected, analyzed, and flagged in real time. At fault zones where ground movement can occur without warning, seismic sensors constantly listen for abnormal vibrations. If any risk is detected, the system can automatically close the tunnel, trigger alarms, and send data to the control center within seconds. Inside the tunnel, high-capacity jet fans maintain airflow, working alongside toxic gas detectors, CO2 sensors, and infrared cameras. Emergency exits appear every 50 meters, while secondary rescue tunnels connect parallel routes every 500 meters, forming a layered protection system against fire, flooding, or accidents. Even lighting is intelligently controlled. LED systems automatically adjust brightness based on vehicle speed and traffic density, preventing glare at tunnel entrances and maintaining clear visibility deep inside. Thanks to this nerve center-like control system, the Tianshan Tunnel is not just a passage through the mountain, but a living structure able to sense danger, respond instantly, and continuously protect human life underground. On the 30th of April 2025, after nearly a decade of construction, the Tianshan Shengli Tunnel was officially inaugurated, becoming the world's longest expressway tunnel, cutting through the rugged Tianshan mountain range. This is not just an infrastructure project, it stands as a symbol of determination, showing how science, engineering, and patience can work together to overcome nature's toughest barriers. From the very first geological surveys to every forward push of a 3,000-ton tunnel boring machine, each step reflects a shared ambition to connect regions, support development, and leave a lasting legacy for future generations. What do you think about this achievement? Can modern engineering and tunnel technology truly help us overcome every geographical limit? Share your thoughts in the comments below. And don't forget to follow Massive Minds, where we explore the engineering wonders that are reshaping our world.